All right. So my name is Tony Shkurti, and I'm a principal engineer with HNTB, and I've worked with HNTB in several places. And I was lucky to spend about 4 years in Milwaukee to work on the Marquette Interchange that you see there in the background. Great project with about 2 million square feet of deck. And the project had five levels of bridges. We called this the spaghetti ball. While I was in Milwaukee, I ended up from a Chicagoan to be a Packers fan as well, and had a lot of fun until I left in 2007. We finished the projects very successfully, and then the first biennial inspection happened. We had about 256 piers on the project, and they were all brand new, of course. You can see in the background of, and I'll show more pictures, but I'll try to show my story in pictures. So there's a lot of slides that I'm going to go through construction as well, so that you understand what's going on. But here's what I'm going to go through. They found during the first inspection, biennial, that's required by federal law for those that are not bridge guys, they found that out of all piers performing great, there was one single pier that didn't look very right, and they called us on. And they were worried, so we got worried. And what happens is that, people's lives are at stake when you hear that there might be shear cracks on the cantilever of a hammerhead. So we got engaged right away, and went on the site and started taking pictures of our own. So this is the Marquette Interchange. I don't have enough time to explain all the ins and outs or how many people use it, but it's a beautiful project right near Miller Park. HNTB has done a few projects here, including the twin cable stays and twin bascule bridges that you see in the background, only half of the symmetrical bridges, and the Marquette Interchange, as we said. All these curved girders were beautiful steel top girders that also match the colors of the nearby Marquette University, that is the Golden Eagles basically, and they use blue and gold for their colors. This was the particular pier. It had interference from below in the clearance of the vehicles. So somehow somebody in the last moments had pushed the pier about 5 feet. So this is the particular pier and the cantilever. You can see they look like hairlines from afar, but they were not very small. Once you put the tracing on them, you can see that, when you went to that, advanced concrete class in school, they told you, I bet, just like my professor said, that it is the shear cracks that you should watch for in concrete. So this was worrisome to us. And looking from a little closer, they're still manageable. You see a fluorescence, but still scary that they were progressing as we move forward. There was also, because the pier had the pier for aesthetic reasons was built in like two panels. They weren't really panels, was mostly ornamental, but they were enforced accordingly. And there was a crack right in the middle of it, so that worried us as well. First thing you do, you go back to the drawing board and you start looking at, hey, what is going on? Why is this pier cracking? And if you look at section AA at the top right of the screen, it looks like it's not reinforced very well. So you go down and you see what's wrong with this pier. Piers were classified in certain groupings, and we had short and long piers, and then we had piers for one lane and pier for 2 lanes. So the cantilevers were longer. And here are some of the piers. So you see that this piers, if you see the types, 2 piers is T5, 6, and 8. 7 is missing from here. 7 somehow was put together with the other piers, with 1 through TS4. Why was that? So We look at it at the regular piers for for Group 1, and they were designed kind of like this, right? But then what somebody got creative, got this pier and shifted it 5.5 feet this way because they realized that there was a conflict in the last few weeks of the project, and they said that this pier has been designed. Let's just use it in here. Just notice, I'm going to go back one slide again. Notice that this is carrying only one girder on the fascia over here, but over here now it's carrying basically 3 girders because it was a integral steel cap. All these three girders, the resultant goes right on the cantilever, which was not designed for and was replaced in a hurry. We couldn't figure out exactly how, 3-4 years after submittal. But this is the piers. We got short piers and we got tall piers. And here's in the bottom, if I was to draw a vehicle coming on the shoulder, you'd see that if this pier was 5.5 feet, it would interfere with that vehicle, just like that. Okay, and that's why that shift was done. So all of a sudden, you got the resultant of all the forces, the reactions coming into the pier with an offset of about 5.5 feet. What that causes is not only the cantilever, the whole thing was in trouble. The shaft and even the piles were in uplift. So you look at section AA of the second group, and you look at the section AA of TS1 through TS4, and you can tell that the reinforcing is not correct anyway. If this was to be even for those 1 girder or 1 girder and a half was much more reinforced. So right there, we knew that there was a problem. But hey, it had not fallen. The beauty of concrete, right? It offers ductility and it tells you that it's in distress. So we were lucky that way. It was carrying live loads for 2 years, and nobody had noticed any serviceability issues. The other thing over here, you can see, that this crack happened right in the middle because it was reinforced with 2 hoops on around. This never happened in the project with steel tubs because we had put on top of it also overall stirrup that took all of that. You can see TS7, this was for top girders that we designed, and you can see that there is a stirrup that envelopes everything. And over here, these are 2 separate stirrups that are not linked together except for that U-shape that goes on the bearing, only at the bearing location. We went through hoops to verify that, hey, it's not fallen. Maybe there is some capacity. You can see that even for self-weight on service load, V only for dead load was at 114%, never mind live load. For moment was below, and V total, 81%. So live load, dead load for the service load, nominal, no factors, we were at 81%. So well below the acceptable. There wasn't much. Then in the pile loads, you can see axial capacity, 0.7 demand capacity. So it was scary. And it was the weekend before Labor Day in Milwaukee. So we got called in, and we never went home for 2 or 3 weeks working on this until we put it back on track. I'm not going to talk much about the logistics and living through it, which was a story on itself, with the newspaper and all the commentators and all that hey, who did this should be hanged in Milwaukee and stuff like that. But at the end of the day, we realized that, hey, you do 256 piers, sometimes stuff like this happens. So any man can make a mistake, but only an idiot persists in his error. So we couldn't go and tell the dude, yeah, don't worry about it. This thing was doomed. So we all make mistakes at work. It's how you react afterwards that matters. And that was our motto. So we got with the DOT right away. We called the secretary. We said, close the ramp until we verify, and we put it back. Now that was waves through Wisconsin and through Milwaukee, right? It was, as I said, Black Friday was coming in, and this ramp led you straight to the biggest mall in Milwaukee. So you can imagine the pressure on the team to do that. So we we looked at this, and I kind of explained how this happened already. You know, missed the big picture basically on the path, and the guy that was doing the final check on the clearances noticed it and notified them, and I think the issue was not escalated properly with the leadership team to address it accordingly. You know, somebody was assigned to just find a solution, a young engineer with little experience, I think, and that's what happened. These were the types of piers we had. The longest was 110 foot tall. The shortest was about 30 plus, and you can see single lane and double lane for the cantilevers. There's 258 piers on the Marquette Interchange. So of course, you know, you screw up one, the DOT asks you to verify every single one of them. So we went and we checked every single one of them, and there was only another one that we had a DB sub that had done slightly under-designed, like for 1 or 2%. That was something that we could repair easy with some FRPs. So we go back and we say, okay, now we took blame. We said we're going to pay for this on our own tab and no cost to the public. So we start studying now. What do we do? First thing is to release the pressure, you know, of traffic. Where do people go? They just were offered a Cadillac and now they cannot use it. So we look at the pier. The pier is right here in the middle. You can see TS7. Where do we put it? Do we put it on the north side, or do we put it on the south side, the shoring tower, to pick up? You know, we decided we're going to replace. Again, the timing is short, but we looked at all the options for repairing it. There was many options, and of course you can do them. But remember, again, we promised and we sold the Cadillac to the DOT, and we couldn't make that a Chevy. We couldn't go back and say, well, sorry, we screwed up, but there's a repaired pier right in the middle of Milwaukee. So also, people may not know, but until about a few years back, you know, although leadership of HNTB is in Kansas City, the president lived in Milwaukee and grew up the firm from Milwaukee. So a lot of ownership on his side is that we gonna replace the pier, period. So we look at options and we decided to put it on the south side because you see there is the utilities and there's issues on the north side. So we came up with an erection scheme and jacking scheme. That's how we're going to do that. We put a steel frame a few feet away where we had to put temporary foundations for it. There is an erection scheme here that we showed. And we started thinking, can we put live load? This lane went from, you can see here that it's going from 2 lanes at the bottom right all the way to single lane without, forget the highlighting for a moment. So it kind of becomes narrow as you get to merge with a highway I-94. So we decided, okay, we're only going to allow 1 lane. We're not going to allow build up, you know, of traffic as they're trying to merge in. And that was the only way we can make it work with the repair and with the shoring tower. We had to study renegade trucks that can get stuck, but only in certain places. We put barrels and traffic control to only allow 1 single lane in the middle so that people can go by with their daily lives. Here's the shoring frame that we designed. We worked side by side. We, as HNTB, hired a local contractor, the most trustable contractor that we had, Zenith Tech, and I became a pretty good friend with the guy working side by side. We designed about 8 W360 were the columns that they had in stock. We didn't want to wait for orders. So all this now, the clock was ticking. You know, we had promised them before Black Friday, we're going to open to traffic back, fully give you back the whole interchange one more time. That's the shoring tower. And we built it. And we built it on, we had to install some new piles on the side and jack the bridge up. So we designed foundation, header beam, shoring frame, jacking sequence, and designed a new pier and continued at the site 24/7. So you can see here the tracing that we did with LiDAR of the existing pier. And here's how we fit the new pier. So we merged on 2 halves of the 2 lane with a single lane pier and that's why it looks kind of irregular, but it still maintains, um, community sensitive design in architectural was very key in the whole project. So we didn't want to lose the pattern. So we matched it exactly, and you can see how we built that. So we gained back the eccentricity of 5.5 feet, but then we had to do the same in the foundation. Here's the design, with a short arm on the right and the regular arm on the left. And the same patterns that we had everywhere else. You see, we have 3 rows of reinforcement there. And actually, after reviews and reviews, Wisconsin DOT said, "Hey, why don't you put 3 or 4 more bars?" Absolutely, as long as they're still within the allowable, um, rebar content, we're fine with that. Now, remember, as I talked, that we had to build temporary piles, tough in the vicinity, of course. Initially, we thought we had to do micro piles, but then the contractor came with a smaller hammer, and they could do it underneath the existing interchange. So here's the pad for the new shoring. Of course, because now you're going to jack at a different location where you don't have no jacking stiffeners. The guys in the building side probably don't use jacking or bearing stiffeners as much, but in our case, they're key because our loads are a little heavy. So we ended up putting a temporary at the location where we were going to jack the bridge and put the temporary bearings. You can see it in here, and we actually had a wedge in here where we installed this, and then we pushed the wedge so that we had full contact mill to bear at the bottom. Here's how it looks before the frame came up. You can see it's about 20 feet away from the existing. We come in and we jack up. We put some wind bracing, of course, you can see, I believe, on the sides of this jacks, you can see this knee bracing and then you longitudinally, but you also can see the wind bracing in the middle girder right there so that it doesn't shift, because the frame was a little, flexible, so we didn't want additional. We built the frame outside, and we brought it inside and we erected it. We actually slid it in. They had some slides they basically strand jacked it sideways horizontally at the very bottom. I think I have a video in here that shows it. Just with a hand jack, they pulled it in. They installed the sliding surfaces to make that easier. And it was a great operation. Everything was going great during the design and erection. So very, very detailed jacking instructions, millimeter by millimeter, basically, with simultaneous jacking at all 5 girders so that we didn't have no differential. And there were red buttons everywhere. There was at least one person watching every jack, basically. You can see there as we're jacking. Finally done. We're protecting the tower from debris as we're going to start demolishing. We're also bracing the tower during erection to the existing pier, and then we start demolition. Demolition continued, of course, and you can see some creative demolition, with raising up the equipment to perform it. And boom, the existing is gone, and the whole bridge is new, and we can take a sigh of relief finally after a month or 2 or a month or 6 weeks of continuous headaches and sleepless nights. Now, as you see, of course, we tried to salvage the existing pile, so we had the 5.5 feet eccentricity in the front, and you can see that we found a pattern that would work by using the existing and just installing 5 new piles. And those are the 5 new piles in the photo as well. You can see that these piles, they were also designed for uplift because there was continuity bars that were embedded, and they were carefully maintained. So we're starting with the construction. Rebar cage has been built on the side. They bring it on site, start building up concrete little by little. Finally, release the jacks. The bearings, we welded them to the girder so that they wouldn't fall down. So when we built the new pier, it was easy to just install them exactly at the same location. We started uninstalling the jacking tower. Finally, there's the new pier of the Marquette, and traffic is back on. Here's how it looks now. You can see the short arm. I remember this every time I go to Green Bay for a game. When I drive back, I show it to my kids as well. So lessons that we learned from this mainly were that, be careful when you group design elements, and who, is using those groupings. It's somebody that has some experience and knows what it means to do that. Clear design summaries. Any doubt, design again. Perform early geometric clash detection. Conventional bridges can be complex. Quality manager and senior technical reviews early and independent from somebody that's not on the job. But it gets really tough in the last 2 weeks or a month when you're still at 70% and the submittal is coming. And this is what causes a lot of trouble. The PM and task lead should do a mandatory cursory review before final. And we do those now. We've implemented all these. Makes me proud how the company handled the problem. We owned it from the beginning. We came out, we gave it, and we gave it back to the public and to the DOT. And actually, the state bridge engineer was asked in the presentation that I attended, this after he showed how great this was handled, and was asked, "Did you end up suing the consultant?" And he said, "Suing them for what?" They came in, they owned it, they paid for it, they hired a contractor. We looked after their shoulders, and everything was done properly. So actually, on the side, he told me that's why you're still doing great in Wisconsin, because of the way you handle and own problems. So be truthful and fair with your client, and it will pay a dividend, basically. They talk to each other as well. So waves went through the DOTs where we'd meet people at AASHTO or at TRB that initially say, "Hey, you guys screwed up in Wisconsin," huh? And you lower your head, and then it says, "No, no, 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 you shouldn't be ashamed of it. We heard what you did. We applaud you." So it did raise HNTB's value in the eyes of WisDOT and other clients in the Midwest and beyond. So that was my presentation. I've never done it this fast, tell you the truth, because the stories are long, and it would take usually 45 to an hour. So I try to cut it as much as I can.